This is an interesting mathematical structures problem, and we're going to go over how to solve it. So first of all, what it means, if C is a subset of A and B, that implies that A and B and C, so the intersection of all three of these, equals C. So this statement here, C is a subset of A and B. You can visualize it like this. We'll do it over here. So it's a funky looking circle. It'll look something like this. So we have A here and B here, and then the middle is C. So this would satisfy this requirement. C, this is the intersection of A and B here, this little eyeball looking thing, and in the center, what would be the pupil, that's C. So every element in C belongs to this intersection area. And that implies that if you take the intersection of all three of these, you're just left alone with C. So if you shaded this one and then shaded this one, got the intersection of A and B, that'll be this area, and then if you take the intersection again, you would be left just with C. And that's what this right-hand side of the implication is. And so to deal with a problem like this, so first thing, there's an equal sign. And when there is an equal sign, it can mean two things. First, C is a subset. The first part, the left-hand side, is a subset of the right-hand side and vice versa. So I've written both of them out here. And I crossed this one out when I previous attempt at making this video, because this is what is known as a trivial solution, and I'll demonstrate that. So if we have A, B, and C, three circles, the intersection of all three of these is a subset of C. So we have these three circles, the intersection of all three of these, well, that's just this space in the middle here. That's just this guy. And what this is saying is that the space in the middle here is a subsection of C, this big circle, and you can see that that's true. Every element in the shaded area is also in the big circle C, and that's true for any intersection. Because you have the AND statement here, this is the AND, it's trivial meaning it's always true, that when you have the intersection of all of these, that is a subset of one of the elements in there. And it doesn't matter how you set this up, even if they're all separate circles, the intersection would be the null set because they don't intersect at all, and the null set would also be a subset of all three of these sets. Anyway, that's beyond topic. So this one is not necessarily true, and in our example here, it's not true. C is a subset of the intersection of A and B and C, and we can see here that here there's elements here in C that are not in the intersection here, and so this is our non-trivial case. So that's the one we're going to deal with. We're going to ignore this guy, and we're going to talk about this guy. So going back to our initial problem, the left-hand side we're going to leave alone real quick. So we're just going to copy and paste that here. And that implies that C is a subset of A and B and C. And that's the one we're going to try to prove. So when you do this in a proof, you would write something like let X belong to C. That implies that X belongs to A and X belongs to B. And then you'd write that for this side too. We're going to skip that. We're going to write lowercase c, and that would mean that we're talking about an element in C, so it's maybe kind of shorthand. So C is a subset of A and B. You can rewrite this as an arrow. If an element is in C, that implies that the element is in A and B, because C is a subset of this intersection we're talking about here. So lowercase c implies lowercase a and b. The wedge here is the same symbol as this one. They mean the exact same thing. I just like writing this a little bit more. We're going to be careful to keep everything in our parentheses wrapped up nicely. Same thing here. I'm replacing the subset with the arrow, and the lowercase indicates that we're talking about elements in the set rather than maybe this whole set itself. I'm not entirely comfortable with the super technical stuff, so don't take my word with it. But anyway, here, how do we deal with these? We're going to use this theorem that A implies B. This is equivalent to saying that not A or B. So why is this true? For this one, let's use an example. Let's say A is you eating poop. I give you a bet. I'll give you $1. If you eat poop, I'll give you $1. And then you get $1. So if A, then B. So I give you this wager. If you eat this, I'll give you $1. So we can create a truth table for this. And this is just demonstrating this equivalency here, kind of intuitively making sense of it. So we have A and B. The possible combinations for this are, okay, you do eat the poop, and I give you the $1. A implies B. You do eat the poop, I don't give you the $1. For this one, we see here that I'm a liar. I didn't hold up my end of the deal. You don't, and you get the $1 anyway. You don't, and you don't get the $1. So you can see here, if it's true and true, then the implication is true, right? Because we made a bet, and you fulfilled your part, I fulfilled my part. This one, you fulfilled your part, I was lying about it, I didn't give you the $1, so this implication isn't true. And these last two, they're called vacuously true. The implication is vacuously true because you didn't eat it, so, well, you can't say I was lying because you didn't take me up on my bet anyway. So that's vacuously true, and so that's how we get this implication. A implies B is not A or B, just like that. And we're going to use that to rewrite this because we can't use these arrows. So we rewrite this one as not C or A and B. We're going to keep it in parentheses. Here we have another implies. We'll rewrite the implies as or. Put a not over this whole left-hand side. Same thing over here. Not C or A and B and C, just like that. Close off this parentheses here. And then we have to use Morgan's law at this point to distribute these nots. So we'll start over here. Not C, that is just C. And here we're using De Morgan's law. So we have to reverse the or and make it an and. C, not C, and not A and B. This side, we don't need to distribute anything, so it's going to be the exact same. Okay, we're going to use De Morgan's law again here. C and not A and B is not A or not B. Proper use of De Morgan's law. And to save time, we're just going to copy and paste this to get our final answer, just like that. So that's what we're looking at so far. And from this point, we can go ahead and make a truth table. And I've kind of set one up a little bit beforehand. So let's look at this and we'll talk about this right now. Why aren't you working? Here we go. Alright, so we have C and then not C. I put that in here because I know it's going to be useful in a second. And then we have A and B. So there's three variables, A, B, and C. So that's going to have 2 to the 3, or 8 rows total. And then we'll have a column for each variable. And I included an extra column for not C. Not C meaning not C, not the National Socialist Party. So we have 1, 2, 3, 4 true, and then to write the next variable, so there's 4 of the same, and you write 2 of the same, and then 2 opposite, 2 of the same, 2 opposite, and you keep on dividing by 2 until you get to true, false, true, false. That was a bad way to explain it, but I hope you can kind of see. Just ignore that second column for now. So first, let's look at this this statement here. We'll say this is C or not A or not B. C and not A or not B. So can we write a truth table for this? Alright, so this is an and statement, so C must be true. So we know that these last 4 rows here, C is false. So right away, because we have that and statement, we can write all of these are false. So C must be true, so we're good because all of these are true. And now either not A or not B has to be true, so one of these has to be false. Here, both of these are true, so that doesn't work. Second row, this one's false. Third row, this is false. And fourth row, this one's false. So we're good for these 3 rows here. C is true for all 3 of these, and there's at least A or B that's false for these 3. So we'll go ahead and look at this other one. Not C or A and B and C. Alright, so the not C, we have these last 4 rows here. They all work because they're all false. The not C, true, 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 true. And since there's an or statement, we don't have to worry about A and B. We're basically good here. And for this, on these ones, none of the not C's are true. So false, 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 so this doesn't work. We have or A and B and C, and here we have A and B and C, and they're all true, so this one is good. And this is taking a second, but we're on the last step here, and I hope you can kind of see the tautology coming together, because in between this statement and this statement, there's an or statement. So the final statement, and I don't have room to write this out, this is F for the final statement here. Either this is true or this is true. Either this statement or this statement. And then if that is true all the way down, that's what's known as tautology, and we have proved that this is correct. So we can do that right now. True, as long as there's a true here, there's a true here, there's a true here, there's a true here, and these last 4 are true. And so we get truths all the way down, and we have established what is known as a tautology. And that's how you prove that this guy is true, beyond just visually. So thanks for watching, hope you enjoyed it.